എൻ്റെ ടോപ്പിക്ക് Wentzel-Kramers-Brillouin മെത്തേഡാണ്. ക്വാണ്ടം മെക്കാനിക്സിലെ ഭൂരിഭാഗം പ്രോബ്ലം നമുക്ക് എക്സാക്റ്റായിട്ട് സോൾവ് ചെയ്യാൻ പറ്റില്ല. പാർട്ടിക്കിൾ നെബോസ്, ക്വാണ്ടം ഹാർമോണിക് ഓസിലേറ്റർ പോലെയുള്ള കുറച്ച് പ്രോബ്ലംസ്, ഐഡിയലൈസ്ഡ് സിസ്റ്റംസ് മാത്രമേ നമുക്ക് എക്സാക്റ്റായിട്ട് സോൾവ് ചെയ്യാൻ പറ്റുള്ളൂ. മറ്റ് ജനറൽ പ്രോബ്ലം സോൾവ് ചെയ്യാൻ വേണ്ടിയിട്ട് നമ്മൾ യൂസ് ചെയ്യുന്ന മെത്തേഡാണ് അപ്രോക്സിമേഷൻ മെത്തേഡ്സ്. To solve a stationary state corresponding to a time-independent Hamiltonian, we use approximation methods such as perturbation theory, radiation method, and WKB method. Perturbation theory is used to solve a problem which is slightly different from a problem that can be solved exactly. By perturbation theorem, we can calculate the contribution associated with the small deviation from the Hamiltonian, exactly solvable Hamiltonian. The other methods are variational method and WKB method, which is used in case where there are no Hamiltonian available which can be exactly solvable. In variational method, we can estimate energy eigenvalues of the ground state and first few excited states of a system for which one has only qualitative idea about the wave function. WKB method നമുക്ക് എനർജി ഐഗൺ വാല്യൂവും വേവ് ഫംഗ്ഷനും ഒരു പ്രോബ്ലത്തിലെ എനർജി ഐഗൺ വാല്യൂവും വേവ് ഫംഗ്ഷനും കണ്ടുപിടിക്കാൻ വേണ്ടിയിട്ട് പറ്റും. If the problem is classical limit is valid in the problem. റേഡിയേഷൻ മെത്തേഡിലും WKB മെത്തേഡിലും നമുക്ക് പെർട്ടർബേഷൻ തിയറിയിൽ പറയുന്നത് പോലെ ക്ലോസ്ലി റിലേറ്റഡ് ആയിട്ടുള്ള ഒരു ഹാമിൽട്ടോണിയൻ, ക്ലോസ്ലി റിലേറ്റഡ് ആയിട്ടുള്ള എക്സാക്ട്ലി സോൾവബിൾ ഹാമിൽട്ടോണിയൻ ആവശ്യമില്ല. ഈ WKB മെത്തേഡ് ഈസ് യൂസ്ഡ് ഫോർ ഫൈൻഡിങ് ഐഗൺ വാല്യൂ ആൻഡ് വേവ് ഫംഗ്ഷൻ ഓഫ് എ സിസ്റ്റം ഫോർ വിച്ച് ക്ലാസിക്കൽ ലിമിറ്റ് ഈസ് valid. WKB method is useful for approximate treatment of the system with slowly varying potential. ഒരു സ്ലോലി വേരിയിങ് പൊട്ടൻഷ്യൽ ഉള്ള പ്രോബ്ലംസ് സോൾവ് ചെയ്യാൻ വേണ്ടിയിട്ട് നമുക്ക് WKB മെത്തേഡ് യൂസ് ചെയ്യാൻ പറ്റും. ഈ സ്ലോലി വേരിയിങ് പൊട്ടൻഷ്യൽ ഈസ് കോൺസ്റ്റൻറ്റ് ഓവർ എ റീജിയൻ ഓഫ് ദ ഓർഡർ ഓഫ് de Broglie wavelength. Therefore, WKB method is viewed as semi-classical approximation. അടുത്തത് WKB മെത്തേഡിൻ്റെ ഒരു ജനറൽ ഫോർമുലസാണ്. m മാസ്സുള്ള ഒരു പാർട്ടിക്കിൾ ഈസ് മൂവിങ് ഇൻ എ ടൈം ഇൻഡിപെൻഡൻറ്റ് പൊട്ടൻഷ്യൽ VFR. The Schrödinger equation corresponding to the stationary state is minus h cut square by 2m del square psi plus v psi equal to e psi. ഇത് നമുക്ക് സിംപ്ലിഫൈ ചെയ്തിട്ട് del square psi of r plus 1 by h cut square p square psi equal to 0 കിട്ടും. Where p is equal to root of 2m into e minus v of r is the classical momentum at r. Also, del square x psi of x plus 1 by h cut square p square of x psi of x equal to 0. If the particle is moving in a region where v of r is constant, potential constant ആണെങ്കിൽ അതിൻ്റെ സൊല്യൂഷൻ, നമ്മുടെ Schrödinger equationൻ്റെ സൊല്യൂഷൻ നമുക്ക് psi of r is equal to a e raised to plus or minus I p dot r by h cut എന്ന് കിട്ടും. If the potential v of r is not constant but slowly varying function of r, then we can use WKB approximation. And using WKB approximation, the solution is psi of r equal to a of r e raised to I s of r by h cut. In one dimension, the solution is psi of x equal to a of x e raised to I s of x by h cut. where a of x and s of x are real functions. Differentiating equation with respect to equation 4 with respect to x, we get d psi of x by dx equal to dA by dx into e raised to I s of x by h cut plus I by h cut a of x e raised to I s of x by h cut into ds by dx, which is equal to dA by dx plus a into I by h cut ds by dx into e raised to I s of x by h cut. Again, differentiating with respect to x, we get d square psi of x by dx square, which is equal to d square a by dx square minus a by h cut square ds by dx whole square plus I by h cut a d square s by dx square plus 2I by h cut dA by dx ds by dx into e raised to I s of x by h cut. Substituting the value of d square psi of x by dx square and psi and psi, that is equation 4, in the Schrodinger equation, in equation 2a, we get the following equation: d square a by dx square minus a by h cut square ds by dx whole square plus I by h cut into a d square s by dx square plus 2I by h cut d into dA by dx into ds by dx into e raised to I into s of x by h cut plus a by h cut square p square of x e raised to I s of x by h cut is equal to 0. Taking the term containing momentum inside the bracket and multiplying by h cut square by a and throughout the term, and again multiplying by a, we get the following term: a into h cut square by a into d square a by dx square minus ds by dx whole square plus p square x plus I h cut into 2 dA by dx into ds by dx plus a d square s by dx square into e raised to I s of x by h cut equal to 0. The exponential term cannot be equal to 0. Therefore, we can rewrite in three-dimensional rewrite the equation in three-dimensional as a into h cut square by a d square delta square del square a minus del s whole square plus p square of r plus I h cut plus I h cut 2 del a del s plus a del square s is equal to 0, in which the first part is real part and the second is imaginary part. And the real part and the imaginary part are separately equal to 0. Therefore, a into h cut square by a del square a minus del s whole square plus p square of r equal to 0, in which a is equal to 0 and h cut whole square by a del square a can be neglected, as h cut is approximately very small in classical limit. Therefore, del s whole square is equal to p square of r, which is equal to 2m into e minus v of r. From the imaginary part, 2 into del a del s plus a del square s is equal to 0. Reducing into one dimensional form, we get equation 9 into 9 as ds by dx is equal to plus or minus root of 2m into e minus v of x, which is equal to plus or minus p of x. And equation 10 can be written as 2 into dA by dx into ds by dx plus a d square s by dx square, dividing by a and throughout by a, 2 by a dA by dx p of x plus d by dx p of x equal to 0, which can be written as 2 d by dx of ln a plus 1 by p of x d by dx of p of x equal to 0, which can be simplified as d by dx of ln of a square p of x equal to 0. Integrating these two equations 11 and 12, we get integral 0 to s ds is equal to integral plus or minus p of x dx, that is s of x equal to plus or minus integral p of x dx, which is equal to plus or minus integral root 2m into e minus v of x dx. Integrating 12, integral d by dx of ln a square p of x dx equal to integral 0 dx, that is ln of a square p of x equal to k, taking exponential on both sides, a square p of x equal to e raised to k, from which a of x is equal to plus or minus c by root of p of x. Substituting equation 13 and 14 in equation 4, that is in the equation of psi of x, we obtain WKB approximate solution of the wave function, that is psi plus or minus of x equal to c plus or minus root by root p of x exponential plus or minus I by h cut integral x p of x prime dx prime. From this equation of the wave function, we can see that the amplitude of wave function is proportional to 1 by root of p of x, that is probability of finding the particle between x and x plus dx is proportional to 1 by root of p of x. And classical particle takes some time to travel the distance dx proportional to 1 by v of x prime, where v of x prime x dash is the speed of the particle. Here we have three cases. In case 1, energy E is greater than v of x, that is classically allowed region. Here p of x is a real function. The most general solution of this case is a combination of psi plus of x and psi minus of x, which is given by psi of x is equal to c plus by root of p of x exponential I by h cut integral x p of x prime dx prime plus c minus by root of p of x exponential minus I by h cut integral x p of x prime dx prime. Case 2 is energy less than potential v of x. This is classically allowed region.